All right. All right, gang. Hey, we have a test. We're done with chapters 1 and 2, which were kind of boring, and chapter 3 is going to be derivatives, and it's going to be exciting. And we're going to learn all kinds of cool things you can do with them and so on. And as a consequence, we've got to get through a test. And after talking to Mr. Punky a little bit and figuring out how we're going to deal with the test and so on, I think what we'll do is we'll use the test as one of our snow days, which means that it will get us off the hook for that, and it's a take-home test.
Okay.
Okay? Because especially considering if I did it on a Tuesday, you wouldn't be there, right, Joe?
Right.
And Scott would never be there. So it would be a take-home test for two of the people anyway. Makes it fair for everybody. I mean, that doesn't mean it'll always be a take-home test when we do a test, but kind of makes sense, right? So we'll burn through one of our snow days and have it as a virtual day or whatever. The test is about half written, and we're going to do the review and stuff like that. And so I will give you the test on Tuesday, which I believe is the date I'm supposed to give you a snow day assignment anyway. Okay? And we will decide when we want the thing due. I'm not going to make the test like bigger than it would have been if you were in the room. So, I mean, it isn't like you need a week to do it because it's some giant, you know, it's the table with a big thud kind of thing, right? I mean, it's going to be...
Oh, I'd be so upset. I'd probably quit this class.
Oh my gosh.
If it
Oh
was
my
that
gosh.
big.
Jared would quit the class.
Praise God.
Anyway. Wow. It is hostile in here. This is a hostile classroom environment. No.
You're just
Stop
gonna
me.
break
We've
your
been
other
down that
arm.
road already. We got enough injuries in this
Stop
class. So, let's talk about the first, the test as we have it. What will happen is, because a lot of the stuff in Chapter 2, I don't have the test written yet. I mean, it's like partially written, but not all that polished yet. We will talk about it, and then I might do a little bit of reviewing about it on Tuesday before I hand out the test to you guys, okay? But this way, on Tuesday, we can start moving forward into Chapter 3 and start learning about derivatives and stuff like that, what we can do with them and so on. This is just a better plan. We don't burn a whole class, and we get rid of one of these snow days.
Oh yeah, that's so fun. Derivatives and all that.
It's going to be fun. Oh my gosh, so much better.
Derivatives are a whole lot more fun.
A lot more fun than all this limit stuff. This limit stuff has been no fun at all. Alright, so let's keep it all moving forward and talk about what we've done so far. Now, the first chapter of the book probably made you feel pretty smart. Because the first chapter of the book was all this stuff that you did to death in like algebra and pre-calculus and trig and places like that, right? So, I mean, gosh, we just sort of picked all this stuff up and, man, we could do... I was looking at, man, some of those assignments in Chapter 1 were pretty big. I mean, I gave you fairly large numbers of problems, and people did them. You know, I mean, it worked out pretty well. So the good news is we can write a test about that stuff. You're going to have open book, open note test. You're going to take it home. You can spend as much time as you want. You're going to get every one of those right. Okay? So the good news is that we just got to get through it. Now, okay, so Chapter 1, the first section, 1.1, was review of functions. Alright, functions. We got this idea. Here's a function. F of x equals, this is that crappy pen. I'm going to hide it over here so we don't use it anymore. Or it'll fall on the floor. F of x equals, this one's also horrible. Poor Mrs. Webster, she has all these junky pens in here. Equals, that's even worse. F of x equals sine of x. Here's a function. How do I know that's a function? I mean, what makes that a function? What is a function? Strictly speaking, in order to be a function, that means each value I put in as input of x, I only will get one value out of it. Okay? We say that the function, it's a function if it passes a vertical line test. Do you remember that term from section 1? That means like if we made a graph of this thing, for any given place we draw a vertical line, it only crosses the function at most once. Doesn't have to cross it at all, but at most once. There are perfectly good things you can draw, you know, using equations that do things like this way. But those would not technically count as functions because any given value of x refers to several different values of y. Or f of x or whatever. They're not functions, strictly speaking. They are passing a vertical line test, therefore they are functions. We learned about lots of different kinds of functions. Not all of that was necessarily in 4.1, but there were all of these ideas, like, for example, there were linear functions, Remember, the linear functions were the ones that had that shape mx plus b, where m was the slope, and this was the y-intercept. And as long as you could get the function into that form by, I mean, not all of them are immediately written that way, but with some rearranging you can get them in that form, then they are linear functions, so-called because they make a line when you graph them. There were polynomial functions. I want to focus on that word for just a second here. What was a polynomial function? What made something a polynomial function? Polynomial functions were the ones that were written as, like, let's say f of x is equal to, like, something x to some power plus something x to another power plus something x to another power plus what, let's make this a 1, plus something. Where they were a sum of terms, each of which was a power of x, including a constant there where that would be x to the 0th power, right? But it was a polynomial function. And there were properties we learned later back in chapter 2 of polynomial functions, like they are always continuous. Okay? There were reasons why we had to separate out those polynomial ones. The polynomial ones, by the way, are going to be great when it comes time to do derivatives and integrals. They're going to be the ones that are the easiest. It's when we're doing more complicated functions like sines and cosines and exponentials and stuff that things will get crazy. Speaking of the exponential functions, remember we had functions that were of some kind of form, like f of x was equal to some number, let's just say 7 to the x power or something like that. Those are the exponential functions. They're exponential because the input to the function, the x, is in the exponent. All right? We will learn and discuss things about this as we go along, but right now at section 1.1, we were basically just talking about them. Let me just pull something up here. The y-intercept, remember, on these functions, that was where we crossed the y-axis. Okay. All these functions would have y-intercepts, or at least might have y-intercepts. I mean, if we had something like a graph of something like this, there is a place where it crosses the y-axis. We didn't spend too much time on it. There were a handful of problems on the test, on the homework set, where you also found the x-intercept, which was the term your book used. The places where you cross the x-axis. That's not really a very common term to use, so, but from like pre-calculus and algebra and so on, you learned about finding the roots or the zeros of these equations, where you were like looking for the values of x, such that f of x was equal to 0. That's what like the quadratic equation and so on were for. Okay? Or, like if you had something linear, f of x equals 3x plus 3. What are the roots of this equation? They're the values of x for which this equation becomes 0. So, like in this case, we could solve this and we find out that when x equals 1, negative 1 rather, negative 3 times x plus 3 will equal to 0. Okay. That's just throwing around some terminology that was in your book. Alright. Hey, we had a vertical line test. This actually wasn't in section 1.1, but just so we're all on the same page here, we also had a horizontal line test. Do you remember the whole business of a horizontal line test as well? Horizontal line tests, we're testing for something related to what we've done so far. We already know it's a function. Okay? But for a function, we have horizontal line tests. Where if we draw a horizontal line at every point, does it only cross the function once? Like this one would not pass a horizontal line test, whereas this one would. Because here, every place we could draw a horizontal line, it would only cross the function once. What was a horizontal line test testing? Horizontal line tests were testing whether or not a function was one-to-one. You might remember that term. It was a one-to-one function. Functions are one-to-one, like this one is not, and this one is. If every value of x goes to exactly one value of y, and every value of y goes to exactly one value of x. Okay. Those had certain properties that we could then later use, like when we were talking about inverse functions and stuff like that. In fact, that's where this thing came from, was the section on inverse functions. All right, so horizontal line test and vertical line test with those two ideas there. All right. Rational, yeah, we got all those things. Nobody gave me much grief about section 1.3. 1.3 was the one that was about trig functions. Gosh, we have a whole semester called trig. Everybody in this room survived that class. And now we just sort of crunched it all down into one day of calculus. I don't know how I feel about that. Okay? One of the things you did on that day was make sure we're getting all back together on that topic of the difference between radians and degrees. I mean, they're perfectly good ways of describing angles. And you had a way of converting between the two of them. Does anybody remember how you convert between degrees and radians? Oh, everybody's a little bit. Day after snow day. How do we change from degrees and radians? Radians, to change them into degrees, you multiply it by 180 over pi, and that'll change it into degrees. If you've got degrees, changing it into radians, you multiply by pi over 180. That is definitely something you did a bunch of examples of in the homework set for a 1.4 or whatever assignment this is. Therefore, make sure you do. I mean, that's not going to be tons of them, but, you know, hey, get some points, right? Here's a unit circle. If I draw some angle on here, starting from standard position where we start this way and we go to this, let's say. Here's our angle. I'll call it theta. That angle is pointing to a place on the unit circle. This spot right here. That spot right there has some coordinate x, y. And in general, it's a goofy number. Okay? In general, it's a transcendental number. Like as in, it goes on forever and never repeats and all that kind of good stuff. But that doesn't mean it doesn't have all kinds of wonderful properties. It is, these points right here are properties of this angle. In fact, that x is called the cosine of that theta, and that y is called the sine of that theta. So if this place was something, I'll give you some numbers here. Let's say this is at -1/2, comma, square root of 3 over 2, which happens to be one that works. Then the cosine of theta is -1/2. And the sine of theta is square root of 3 over 2. That's what sine and cosine are by definition. They are the coordinates of the point that angle points to on the unit circle. But of course we do all kinds of other things with them. I mean, you all survived trig, so you know that there's the whole business of using them about triangles. You know the whole thing about, you can use them to talk about waves, you know, like sine waves and cosine waves, and you know the whole thing about tangents and cotangents. In fact, that all comes up again in this section. The good news is, about this section, even though there's a lot of stuff in here, it's all pretty neatly summarized up in little tables. There's little tables that explain how tangent is related to sine and cosine, or cotangent, or secant, or cosecant. Most of which I don't really care all that much about. Okay? There will be problems once we're starting to do derivatives and integrals, where like we're doing the integral of tangent, or we're doing the derivative of tangent. Okay, but you know what? Life is short. And the universe is full of things that behave like sines and cosines, and not that full of things that behave like tangents and secants and cosecants and cotangents. So I, being a scientist, like the sine and cosine stuff a whole lot better. You know what I'm saying? Everything moves as sines and cosines. Pendulums, springs, weather patterns, tides, all move as sines and cosines. I don't really care that much about tangents and cotangents and secants and all that kind of stuff. Yeah. When we hit a problem or two, we'll need them, but I'm not going to get... Your test would be 35 pages long and hit the table with a thud if I included all that stuff, right? It would be less. In that section 2, you had all kinds of problems where you were simplifying expressions that use these trig functions. There were a lot of problems in that section that were things like tangent squared of theta sine theta. And it would say, simplify this. And your book had some like little table of trig identities and so on. Okay. We can kind of mostly just keep track of what do we mean by tangent and what do we mean, and maybe keep track of one key identity, namely the whole business about sine squared of theta plus cosine squared of theta equals 1. And between those two things, we can probably get this all worked out. Like, for example, tangent squared of theta times sine of theta. Well, tangent is sine over cosine. So this is the sine squared of theta over cosine squared of theta times sine of theta. So this is sine cubed of theta over cosine squared of theta. Okay. Whatever, I just made that problem up in my head. The ones in the book were more clever. Like, oh, look, it all works out to 1. Or, it all just works out to cotangent, or something like that. Okay, I don't happen to have that. But they often had things in them that required this. Let me just see here, for example. How about 1 minus cosine squared of theta over cosine squared of theta? Okay, here's 1. Alright, well from our, this one identity, by the way, that's just a fancy way of saying the Pythagorean theorem. It's not how Pythagoras did it, but it could be. From that, you can see how this thing on the top becomes sine squared of theta. And a sine squared over cosine squared, that's tangent squared of theta. So this whole thing becomes tangent squared. That's what I mean by simplifying. Okay? And I'll have some guidance on the test if there's any problems. There will be problems with that. You know, like, it probably would be more like, show that this expression equals tangent squared of theta. Okay? Because if I just tell you to simplify it, who knows where we would go with that. Alright. So that wasn't so bad. You were okay with that stuff there. That day we did inverse functions. Inverse functions is a term we throw around a lot in math classes. They've been doing inverse functions over in trig right now. Where like the inverse function of sine is the inverse, the inverse sine, also known as the arc sine of theta. Well, that's kind of a tautology. If you didn't know what an inverse function was, how does that help you? Similarly, we learned in pre-calculus that, like, for another function, e to the x, its inverse function is the log of x. And they all have this nifty property that these functions cancel each other out. So, like, the arc sine of the sine of theta is just theta. They cancel each other out. Or e to the log of x is just x. They cancel each other out. But in this section 1.4, we actually did something that will prove to be useful once we get to derivatives and integrals and stuff like that. We actually figured out what you're doing here. And it was easiest to think it through with pretty simple examples. For example, what if your function, f of x, was something like 7x plus 1? That's a function. It has an inverse function that kind of undoes it. And you had a set of steps in the chapter as to how you find it. What you do is you write this thing as like y equals 7x plus 1 and solve for the x. So you go y minus 1 equals 7x. So y minus 1 over 7 equals x. Then play the big switcheroo and switch the y's and the x's around. Y equals x minus 1 over 7. That is the inverse of this. That game can be played with more complicated functions, like big old polynomials and stuff, but it gets to be a mess fast. I think you did one problem like that on the homework. We are not going to go nuts with problems like that get more complicated. In general, once you have these guys, you've figured out a function and its inverse, they have an interesting property. I mean, if I draw myself a little diagonal line right here, remember they had an interesting property. A function and its inverse have graphs that are like the reflection of each other. So like, if your function f of x looks like this, then its inverse looks like this. They're kind of reflected across that diagonal line. So you can graphically identify. So a fair thing when I was looking through like sample tests and stuff like that was, you know, like for example, they had some where they put a couple of different things up here and they asked you which one of these could be the inverse of the other one. That kind of thing. Okay? Just graphically, how could you tell? That seems, I'm not sure I would do it exactly like that when I wrote the test, but on sample tests they provide, that's how the kind of thing they did. Alright? Alright. What else happened in chapter 1? I think there's only one other section in there. Oh, it was those logs and exponents. The logs and exponents thing, I could write a whole test on that. Hell, I have written whole tests on that because you guys all survived, not necessarily with me, pre-calculus. And in pre-calculus, there was a whole chapter about log and exponential rules. It was about the time I started working here, so like part of it had been taught before I got here, but it was a whole chapter. There's all these log rules and stuff like that. You guys all seem to do those rules pretty straightforward. You know, this is the whole business of like e to the a times e to the b is the same thing as e to the a plus b. Or the log of a divided by b is the same as the log of a minus the log of b. And you have those rules and nobody really complained all that much about them. In the current draft of the test, there's not much of that. Here's the deal. You've already been tested to death on this stuff in other classes. And B, there will be later times in this class where you're going to be using these rules. Because this kind of stuff happens all over the place. Again, derivatives and integrals and stuff like that. There'll be plenty of other times for you to show me how bright you are about this stuff. So I'm inclined not to go too nuts with this stuff. In fact, let me look real quick at the current draft of the test. What is that? Check section 1.5. Currently on section 1.5, there's only 2 questions. At the present time, they're both pretty easy. Like, I actually have a note there that says, I'm not even sure it's worth asking these. Because, I mean, there's a strategy when you're writing tests, right? There is something to be said for writing a question that's so easy that anybody who gets this wrong, that's useful to know. If I write a question that says 2 plus 3 equals what? If there's anybody who gets that wrong, that's information I need, right? Right? If there's somebody who doesn't know what 2 plus 3 is, I need to know that, okay? On the other hand, at some point, just from our experiences in the class, I know you all know 2 plus 3, right?
2 is fine.
There you go. Wait, what? And therefore, I don't really get all that bent out of shape about those kinds of questions, right? So at the present time, the kind of questions I have written are kind of like that, okay? Everybody's going to get that one right. At some point I have to ask, is it worth asking that? Alright. Especially in a giant class, we don't really know the people. I used to teach Introduction to Atmospheric Sciences to a room of 300 some students. You don't know those people. They don't know you, which is weird. You get a pizza delivered, and the guy's like, hey, you're my teacher. Well, I don't have that idea who the hell you are, right? In a class like that, you do need to write some questions that, okay, you got to identify, because out of 300 people, there's going to be some people who don't know 2 plus 3. Well, not that, but you know what I'm saying, the basic stuff. There's 7 of you. I know you all. I'm pretty sure I don't have to ask the really basic baby questions. But you never know. Alright, so chapter 1 probably made us feel pretty smart. Man, we could do all those problems, no problem. Then we moved on to chapter 2, and things got a little bit flakier. Chapter 2 has not been my favorite part of the book. Okay? As I'm going forward and looking at things coming to come, the book gets a whole lot more on my side about a lot of things. So we're going to kind of keep things... The questions I'm going to be asking you, you should be able to find examples from your homework and stuff like that that are similar. Let's put it that way. Okay? Chapter 2.1, a preview of calculus. This was the day that I couldn't even really find good questions in the end of the chapter. I think you only had like 3 problems or something that day. Now, of the stuff that we did in section 2.1, one of the things that I think is a key take-home thing that we're going to need to be able to remember when we start chapter 3 is that whole business of secant lines and tangent lines. This is a completely unrelated idea to the ideas of secants and tangents from the trig stuff. This was about, okay, remember when we had just a linear function, talking about the slope of that function is no big deal. We know what we mean by the slope of a function. But it is a whole lot more complicated to ask about what is the slope of a function that isn't linear. Despite the fact that we are all in great agreement that slope still means something. Clearly a car right here, apparently it's a truck, has a very important idea about what slope means, right? And a very different idea about it than what a truck right here is thinking. Well, that's a really terrible truck. Okay. Clearly, slope means something, even though it's not a flat line. And we said, well, you know, I kind of get what I mean by the slope at this truck here. I mean, I could talk about the value right here, and I could talk about the value of this function right here, and kind of make this little secant line. Where the secant line had a certain slope. That slope of the secant line is kind of what I mean by the slope of the function at that point where the truck is. Where that slope was the value at some point. I can't remember. I can't remember which one they called X and which one they called A. I think they called this one A and this one X. The value at some point A minus the value at some point X divided by the difference between A and X, that was the slope. It was how much the change in the F versus how much the change in between X and A. That was the slope of the secant line. That isn't exactly the same as the slope of the tangent line. The tangent line, remember, only touches the function at one tiny little spot. That's going to be about derivatives, which was the chapter 3's topic. But the slope of the tangent line is a little bit different than the slope of the secant line. What we in fact learned was that the slope of the tangent line was a limit. The slope of the tangent line was going to be the limit as x approached A of this thing. The problem, of course, is this is one of those ones that blows up. It's one of the ones where it gets to be 0 over 0. As the difference between x and A gets smaller, this thing here, again, I don't remember if it's A minus x or x minus A. I don't remember which way they wrote these students around. It doesn't matter. The denominator gets to be 0, but the numerator gets to be 0 too. We're going to need the magic of calculus to figure this out as to what's going on here. We also, in that section, did this idea about what about the area under the curve, and we talked about dividing that up into little rectangles. Here's the deal. That's actually super important when we get to like chapter 5. But that's far enough in the future that we're almost certainly going to have to review it when we get to that point. I am not going to test you on that thing about the areas under curves, the little rectangles. That doesn't seem, don't get me wrong, it's hugely important, but we're so far. That'll be like April when we get there, okay? There's no point going nuts about that just yet. So really, that's the only thing we could do from section 2.1. Section 2.2 was this idea about limits. Limit can be a really simple idea. I mean, in lots of cases, the limit as like x approaches a of some function f of x is just the value of f at the final thing. In other words, you know, hey, I've just got some function, and I say, here's some value a, here is f of a. The limit as I come in from this side, the limit as I come in from that side, as I put smaller and smaller difference between x and a, it's just converging on this spot right here. In fact, that turns out to be the truth for just about everything. Only some weird cases it wasn't. But for like linear expressions, polynomial expressions, and rational expressions, as long as the denominator wasn't going to 0, then things got different. You know, the trig function, stuff like that, all those limits were actually pretty straightforward. Your book decided to be tedious and pedantic and make you go through the process of proving these things. Over the course of every section of chapter 2, it got a little more formal, until eventually in 2.5 or whatever, it actually even did the delta epsilon definition, or epsilon delta I think is the way they put it, of this, which is the very formal way of deriving. But you could see what was happening here. That being said, there were functions this doesn't work. I mean, there are functions, for example, where we could define it work in a more complicated way. There were piecewise functions where like, that's how our function is defined. At a, I realize I didn't draw this very well. At a, there's a perfectly good value of f of a. It's this thing. And as it happens, in this case, that is the limit as x approaches a from the right. And there is a limit as x approaches a from the left. It's just not equal to each other. And remember, for the limit to exist, both of those had to be true. This had to be equal to each other. There had to be a limit from the left and a limit from the right. So like this one doesn't have a limit at a. It does have a limit from the right, and it does have a limit from the left, but because they don't match, it doesn't have a limit. I realize that's confusing the terminology. They should come up with a better word. Okay? The limit means you've got both of them, both from the left and the right exist, and they match. Okay? You had a whole list of ways in which this could go wrong. Because you needed to have functions that were continuous. And you had a whole bunch of ways in which functions might not be continuous. I don't remember all that vocabulary at the top of my head. I'm going to have to review it before I write the test questions. But there were like the ones that had a graph that had like a little gap in them. You know, they were defined everywhere except one little stupid place where there's a gap, because you ended up with like a denominator that was 0. Okay, what was that called? It wasn't a gap. What did they call that? Discontinuity? No, I can't remember. Anyway, you had all those. Those will definitely be on there. In general, continuity strikes me as one of the more testable things we did in Chapter 2. In contrast, like delta epsilon definitions, which I can't really think of how to write a question about that. Okay? I mean, I even looked back through like other tests that other teachers, you know, again, sample questions, and even their questions, I'm like, well, that's kind of stupid. That doesn't really tell us anything about delta epsilon. But continuity, we had all kinds of tests of continuity and so on, and ways it could be discontinuous. That struck me as a good stuff. But you can see where we're heading with this stuff now. You can see that as we move into chapter 3, we're going to be talking about the derivatives of these functions. The derivative being a way of talking about what's the slope of this function at each point. And it's going to matter about what's going on at places where there are discontinuities. And isn't necessarily a deal breaker. It's often the case we can still do useful things like derivatives and integrals where there are discontinuities, be they little gaps, or be they this kind of discontinuity where there's like piecewise parts or whatever. Sometimes we can and sometimes we can't make it work. And since so many real-life things have, real-life functions have these discontinuities, we're going to have to be able to make this work. All right. The short take-home message. I think the majority of the points on this test are going to come from chapter 1. Okay? Because that's a library of skills that you're going to need in order to succeed in later chapters. Right? When we're learning a chain rule for derivatives. I see that that's coming up in section 3.2 or something, or 3.4. Okay, chain rule. There are going to be chain rule problems. I know you don't know what chain rule is yet, but there'll be chain rule problems involving things like polynomials, exponentials, trig functions, etc. You got to show to me that you can do all that stuff. On the other hand, that limit stuff is mostly going to be about how we end up defining derivatives and integrals and stuff, and then we're going to move on past it. That doesn't strike me as being the most points we need. The discontinuities and stuff could be quite important. That secant line stuff could be quite important. There will be places where that comes up relatively soon in like section 3, chapter 3, so we do need to test on that. Okay. So, on Tuesday, the next time we meet, I'll have the test with me. I'll be able to give you a little bit more specific review. We can answer some questions and stuff. I'll probably give you the test at the end of the period. But on Tuesday, we'll also start section 3.1. Obviously, I can't make it so that your test and the homework are both due on Thursday. Well, I mean, I could. But you wouldn't like me very much. And so we'd be done. How do you feel about that?
Sounds good.
Sounds good?
Sounds great.
All right, then I'm going to stop the camera real quick here.